So I just introduced before the break. I just introduced your 2D mole circle and 3D mole circle. So the next thing is what to do with this value, what to do with these principal stresses, right? So we have calculated two values, right? One is minus 28.138, the other one is 13.142. So only until now, okay, only until now, then we can determine the factor of safety, which is equal. So if we were to look at the table, right? So for example, we pick the first one. Okay, we pick the 250. We assume that our material is a structural steel. Okay. So we assume tension and compression have the same magnitude. So it's at 250. So now then you can put minus 250 times 10 to the power 6 divide by minus what? Minus 28.138. Minus by 28.138 times 10 to the power 6, right? So your factor of safety, okay, is equal to 8.88. Okay, 8.88, right? So 8.88 is very high. So if you look over here, maybe you can use material with lower strength, which you don't, okay, which we don't have, okay, and possibility that the structure ASTM A36 is the cheapest steel around, okay, and your factor of safety is so high, so your structure is sound, right? So if I want you to recap what we have done, right? We found our loading, normal stress, normal force, shearing force, bending moment, okay? And then we look into shearing, right? We look at the shear stress. We calculate the shear stress for element A and element B. Then today, we calculate our what? We calculate our normal stresses today, right? So today we spend time on normal stresses. Okay, what I'm trying to tell you is this. Whatever we learn from week 3 onwards, we apply. Okay, and then after that, you still can. We are not done yet. Not done in the sense that we still don't know how to calculate the factor of safety. We have not done 2D and 3D mole circle yet. Okay, so you can see the build up of the topic. Okay, so we have to understand what is normal stress, shearing stress. Okay, and then we use 3D mole circle. Another thing that we have not done is we have not done buckling analysis. Right? Remember what we learned on week 1, right? So if in real life, okay, if the length over here or the geometry of the length is very high, right? Then unfortunately we have to carry out what? Buckling analysis. Okay, and it's not difficult. You know how to do it. So if we were to quickly look into buckling, the formula. Come on, does all this look familiar to you guys? The answer is yes, right? Okay. Some of you are like, oh no, not again, right? So in buckling, I can do this quickly for you or for us. We need to find out what is our critical load. Okay, just quickly. Okay. So we know that we have to apply. Let's see what formula. The formula we have to apply is critical stress is equal to pi square E over LR squared. So I'm going to make an assumption that is under centric loading. Okay, I'm just going to make the assumption. Okay, so we are going to assume, or I'm going to assume centric loading. Okay, just very quickly, if you have to do complete analysis like an engineer, so we have just to assume. So we just put down buckling analysis. right? So we are going to assume centric loading. So the formula that we have to apply. So I want to find the critical load. So I'm looking for the formula for the critical load. Okay, we're going to find PCR equal to pi squared EL. So we're going to use this critical load. Okay, so I'm going to copy. And then I'm going to come over here. We're going to look at this formula. Okay. So we know that our pi squared. So we know that PCR, our critical load, is equal to pi squared, Young's modulus of steel, multiplied by I. So we are going to pick the lower I. The lower I will induce buckling first. So we're going to pick the lower I. So it's 9.01. Okay, so we just come here to put in 9.01 times 10 to the power minus 6. And then the L squared, one end is fixed, the other one end is free, one end is fixed. So our L, right, our L1 end is fixed, the other one is free, so it's equal to 2L. So we go back here, we consider 2L squared, so 2L squared. So this is equal to pi squared multiplied by 200 times 10 to the power 9, multiply 9.01 times 10 to the power minus 6. So the 2L, our length, is equal to what? Our length for our structure is equal to 0.5 plus 0.1, so it's 0.6. 0.6 multiplied by 2 is 1.2, so it's equal to 1.2 squared. So we calculate our critical load, okay, 200 power 9 times by 9.01 power minus 6 times by 3 pi squared, and then divide by 1.2 squared. Okay, so the structure we only need to consider buckling. Okay, if our critical load or this is equal to our PZ. So i.e. if PZ is greater than 12.35 times 10 to the power 6 Newton. Okay, then buckling analysis or then buckling will occur. Okay, so this one I make an assumption due to time. By right, the assumption made is centric loading. Okay, so we can also do eccentric, right? Because one view, right? One view, if I view from here, it's centric. If I view from here, it's eccentric. Okay, so this is the full scope of a structure designer. Okay, and unfortunately, if you go to companies that do structure analysis, okay, the person that need to know all this is usually the principal engineer. So there's only maybe 2 or 3 principal engineers in a company. Okay, but I'm training you. So if there's a possibility of you bring a principal engineer, you can do all this. Okay, right. So don't worry about the buckling part. I will not test you anymore on buckling. Okay, but I will still test you things about normal stress and shearing stress. Okay, okay. So that gives the how all these small topics are linked into one this big picture. And we are not done yet because now I'm going to go into a topic. Okay, you've seen it before. We are going to go into the introduction of 2D Mohs circle. Okay, So I've drawn for you what it looks like, okay? And I'm going to do it again, okay? But in a easier manner, okay? Easier means in the context that, okay, there are not so much stuff first, okay? We're only going to look at 2D first, okay? Okay, but before we do 2D, there are some terms that I need to teach you, okay, before we can do anything. So in Mohs circle, there are stress state that we need to know. Okay, so we have plane stress and plane strain conditions. Okay, you look at plane stress or plane stress. So if we have an element, so I'm going to construct my element. So you've seen this before. In real life, everything is in 3D. Okay, nothing is in just 2D. We don't live in a flat world. So this is our X, and this is our Y, and this is our Z. So if this is our element, now an element is never a cube, okay? It always has a face that is bigger, a surface area that's bigger than the rest, as you can see down here, right? So what do I mean by that? So over here, this surface is on our XY plane, and it is the largest surface area. So we call this in plane. Okay. Then this plane over here, this is our YZ plane. Now, why this is our YZ plane? Because if you look at the surface, I just label YZ plane. This surface on this transformation over here, this is our YZ plane. Okay. It's not difficult, it's just getting used to it. Okay. So the YZ plane is not the largest surface area. So this is our out of plane. Okay, so likewise for this case, this is our XZ plane. And again, this is our out of plane. And on each plane, we have normal stresses acting. So this is going in the X direction. This is our stress X. This is going parallel to the Y direction, normal stress Y. And this is our normal stress Z. Okay. So now you know what normal stress look like, and you also know what is in plane and what is out of plane. Okay, and then from here, I'm going to tell you what is a plane stress condition. Okay, I'm going to draw. In a plane stress condition, okay, in plane stress, it's usually stress X and stress Y is not equal to 0. However, stress Z is equal to 0. This is what we call plane stress condition. Or you can have stress X and stress Z is not equal to 0, but your stress Y is equal to 0. Or you have a condition where stress Y and stress Z is not equal to 0, where stress X is equal to 0. So this is what we call a situation where we have a plane stress condition. Then the next one is we can also have what we call a plane strain condition. Now, plane strain condition is not the same like plane stress. Now everything is in strain. Okay. So in plane strain condition,